Okay, so assume that we have two coordinate system. One coordinate system we call x1, x2, x3. We call it the old coordinate system. It has basis vectors e1, e2, e3. And we have another coordinate system x1 bar, x2 bar, x3 bar, which we call the new coordinate system. And it has basis vectors e1 bar, e2 bar, and e3 bar. Now these two coordinate systems are rotated with respect to each other. So x1, x2, x3 is our old coordinate system, and the new coordinate system is rotated with respect to the old coordinate system. Now you probably know that if I have a vector defined u here, the components of the vector in the old coordinate system and new coordinate system are going to be different. In a similar way, if I have the components of a second order tensor in the old coordinate system, the components in the new coordinate system are going to be different as well. Now, it turns out that if I know the components in one coordinate system, suppose in x1, x2, x3, I know the components of a vector or the second order tensor, I can find the components in another coordinate system which is rotated with respect to each other, provided I know something called the transformation tensor Q. The transformation tensor is an orthogonal tensor, which means that the inverse of the transformation tensor is the transpose. And most of the time for rotations, determinant of Q is equal to 1. We will also look at some cases where we have deflection, where the determinant of Q will be equal to -1. Now, this is how the components of the transformation tensor is defined. The components of the transformation tensor Qij are the direction cosines of the old basis vector I with respect to the new basis vector j. So it is the dot product between EI and EJ bar. EJ bar are the new new basis vectors, and EI are the old basis vectors. So we can write EI bar equal to QEI, that's possible, and EI is equal to Q transpose EI bar, because if you take Q to this side, you get Q inverse, but Q inverse and Q transpose are the same, so you can replace the inverse by the transpose, and this is what you will do to get the old coordinate systems in terms of the new coordinate system. And here the new basis vectors in terms of the old basis vectors would be given by this. Some books use the opposite of this, so they use the new with respect to the old, but we will stick to this. So the new basis vectors are Q times the old basis vectors, and the old basis vectors are Q transpose times the new basis vectors. Let's figure out how these basis vectors, how this transformation is computed, transformation tensor is computed. Let's take a problem where we do a transformation for a 2D rotation of the x1, x2 axis by an angle theta about the x3 axis. So let's okay. So what we have is old coordinate system x1, x2, and x3 is out of the plane, and we have rotated it to x1 bar, x2 bar by rotating about the angle, rotating about x3 by an angle theta. Okay, so when we do this, the x3 direction doesn't get changed. The x3 and x3 bar directions are the same, but x1 bar and x2 bar change from x1 and x2. So the definition is Qij is equal to cos of new with respect to the old. Oh, we have used the opposite. Okay, okay, let me see. It's making a mistake here. So we are going to use cos of old with respect to new. This is what we have used. Now Q11. Okay, firstly Q33 is 1 because the angle between E3 and E3 bar is 0. Q13 is 0 because the angle between E1 and E3 bar is 90 degrees, and similarly Q23 is also equal to 0. Q31 is 0. Q32 is also 0. Now Q11 is cos of angle between this and this, which is equal to theta. Q22 is angle between this and this, which is also equal to theta. So this is also cos theta. Q12 is the cos of the angle between E1 and E2 bar. So this is your E2 bar, and E1, the angle is this. Okay, so that is cos pi by 2 minus theta, which is equal to sin theta. Similarly, cos Q21 is equal to cos of E2 in terms of E1 bar, which is E2 in terms of E1 bar, which is cos pi by 2 plus theta, which is equal to minus sin theta. So this is how you will do this two-dimensional transformation, and the transformation matrix would look like this. Transformation matrix would look like this, and the final matrix would be of this form. Okay, if you use the old first and the new, old with respect to new notation for Qij. If you use the other one, these two would get interchanged, these two would get interchanged, and therefore these two would get interchanged. Okay, we will not do that. Now, from the basic definition, uh, let's say how the components of a vector V uh, transform with Q. So we want to find the new components of vector V with respect to the old component. So the new components are Vi bar, which is given as V dot Ei bar. So this is how we extract components of a vector in a particular direction. So Ei bar is the direction, and this is Vi bar are the components. Vi is V dot Ei, but then Ei bar and Ei are related by Q. So in place of, so I write Vi bar is Vk Ek, this is Vk Ek, dotted with Q times Ei, which gives me Vk Q Ki. So if I do Vk Q Ki, I get the new components of the vector. Similarly, I can do the ulta of this, and I can do Qik Vk bar to get the old components in terms of the new components. So this gives me the new components in terms of the old components, and if I use this, I get the new components in terms of the old components. And the way I get the components of a second order tensor are exactly analogous. So what we start with is the fact that the ijth component of a second order tensor T, this is how we extract it. We pre-multiply by Ei, post-multiply by Ej. Similarly, if I want in the new system, Tij bar are the new components of the tensor, and I pre-multiply by Ei bar, post-multiply by Ej bar, and now I want a relationship between the new components and the old components. So recall that Ei bar is Q times Ei. I use that fact. I use the fact that Tij bar is Tij bar contains this T, which is TPQ EPEQ, and then I replace Ej from this equation here. I replace Ei bar from this equation here, and I get everything in terms of e's, not e bars. So I take this equation, I replace ei bar here, I replace ej bar here, I replace t here, everything in terms of the e's. Finally, I do the dot products. I'm not doing it, I'm just leaving it for you, and then this is what I get. This is the old components in terms of the transformation tensor, gives you the new component. Similarly, if you want to do the opposite, you have to start from here. You have to express EI in terms of EI bar, EJ in terms of EJ bar, and T in terms of T bar. Everything would be in terms of E bar on this side, and then you will end up getting this equation. So this is easy to remember. You have to remember it for any order tensor. Tij bar, the new components, are Qki, Qmj. So ij appear later, I appears here, j appears here, times tkm, these are the old components. So k and m appear earlier as the first index, and I and j appear as the second index. So whatever is on the left appears on the second index, whatever is on the right appears on the first index. It's the other way around when you want to express the old in terms of the new. When you express the old in terms of the new, it's the other way around. Okay, so this can be extended to a tensor of any order, and for a nth order tensor, this is what you will get. Whatever is here, whatever are the indices here, they appear later, I1, I2 up to In, and the indices here appear earlier, Q, K1, I1, K2, I2, Kn, In, they appear as the first index. So this is the generalized form of for an nth order tensor, and you see that for a second order tensor. For a second order tensor, this is what you see. This is the special case for the second order tensor, and this is the one that we will use the most. Okay, now there are tensors whose components do not change if you rotate them. So you do this QKI, QMJ, AKM, you do this operation, but after the operation, what you get is the same tensor back, same components back. So the components of this tensor does not care about the rotation of the coordinate axis. Such tensors are called isotropic tensors. These are special kinds of tensors whose components do not change if you rotate the coordinate axis. Okay, so we will stop here. This is all that we had to do for tensor algebra. We will start tensor calculus in the next class, and that would be next week. Remember, you have a quiz on the 7th, and that quiz will consist of what you have thought, what I had asked you to think about this combined bending torsion problem, plus summation convention and the stuff that we have done so far in tensor algebra. Okay.